We're now going to consider inclined planes. Inclined planes are very useful systems to consider because on an inclined plane, the acceleration is less than the acceleration due to gravity. So it was for this reason that Galileo studied inclined planes, and he was able to show, before we had cameras and good motion sensors, that the acceleration due to gravity was a constant in lots of locations. So let's consider the forces acting on a body which is on an inclined plane. So when I let go of this cart, we've just got a couple of forces acting upon it, and these are forces that you've already learned about. We've got the weight force, which is acting vertically downwards, and we've also got the normal reaction force, which acts perpendicular to the surface, which is the plane in this case. So in this case, the reaction force is not in a direction parallel to the weight force, instead it's perpendicular to the plane. Now, if I let go of the cart, it accelerates, and clearly it's accelerating in a direction which is parallel to the plane. There's no acceleration perpendicular to the plane. If there was acceleration perpendicular to the plane, the cart would either be coming up off the plane or to be somehow falling through this track down to the table below. And obviously that's not happening, so the acceleration's all in a direction which is parallel to the plane. So we can actually calculate what this acceleration is. The acceleration is due to the resultant force. So that's just from Newton's second law, which tells us that the mass times the acceleration is equal to the sum of the forces, which in this case is the weight force, which is vertically downwards, and the normal force, which is perpendicular to the plane and upwards. So we can draw them as vectors like this. We need to add these vectors head to tail, and the resultant vector is the mass times the acceleration of the cart. So we can use this to show that the acceleration is equal to g sine theta, and the normal force in this case is equal to mg cos theta. So let's just show that on the screen capture now, just to make sure that you're very clear on that. Okay, so I've got my mass on an inclined plane here, and there's two forces acting on it. I've got the weight force, mg, pulling it down, and then perpendicular to the plane, I've got the normal force. And then what we've done is we've added these two head to tail. So we've got mg going down like this, and then our normal force going up like this. And what we want to do is work out what's this angle in here. So we can use a little bit of geometry to show that. So this blue triangle here, this light blue triangle, is a right angle triangle. Down here we've got 90 degrees because mg is acting vertically downwards, and this line along here is a horizontal line. So that tells us that the angle in here is equal to 90 minus theta, because the angle sum of a triangle adds up to 180 degrees. Okay, so let's continue our vertical line up like this. Now here we've got two vertically opposite angles. And so if this one here is 90 minus theta, it means that this one here must also be 90 minus theta. Now when we drew n, we said that it was perpendicular to the plane. So if it's perpendicular to the plane, it means that the angle between the plane and our vector is 90 degrees. So we've got 90 minus theta is this angle in here, and we've got this whole big angle is 90 degrees. So that tells us that the angle in here must be theta. So the angle which our normal force makes with our line, which is vertically downwards, which is the direction of mg, is theta. So we can write that this angle in here is theta. Okay, so we know that our acceleration is our resultant force and that it is parallel to the plane. We observed that. So the angle between the perpendicular to the plane and the parallel to the plane is 90 degrees. So our triangle here is a right angle triangle, and this is a force diagram. So this resultant side is given by the mass times the acceleration. So what we can do now is use trigonometry to work out what the acceleration is. So we can use sine theta, which is equal to opposite over hypotenuse, and in this case the opposite is MA and the hypotenuse is MG. So the m's cancel out, and we can rearrange this to get A is equal to G sine theta. Now, the other thing which it would be good to find out is, well, what's the magnitude of the normal force N? So we can use this same triangle and say, well, cos theta is equal to adjacent, which is N, over the hypotenuse, which is mg. So rearranging this, we end up with N is equal to mg cos theta. So now we have the magnitude of the normal force, and we know that it's up and perpendicular to the plane. So we just saw one way to see that the acceleration of the cart was given by g sine theta. But there's another way which is sometimes a lot easier to do. So the other method involves breaking all the forces into components parallel and perpendicular to the plane. So let's consider the normal force first of all. So the normal force is up and it's perpendicular to the plane. So this doesn't change. It's just the normal force, and all of that normal force is perpendicular to the plane. The normal force parallel to the plane is equal to 0. Okay. On the other hand, the weight force, which is going vertically downwards, has a component parallel to the plane and another component which is perpendicular to the plane. So let's look at the screen recording now, where we'll split that into the two components. Okay, so what I have here is a diagram showing the weight force mg vertically downwards. And what we want to do is we want to split this into two components. So we want a component parallel to the plane like this, and a component perpendicular to the plane like this. And these two components, when they add together, they have to give mg as our resultant force. Okay, so we'll need to do a little bit of geometry again. This is much the same geometry as we did last time. So this is a right angle triangle here. If we've got theta down here, then this angle in here must be 90 minus theta. These two are also perpendicular to each other because one is parallel to the plane and one is perpendicular to the plane. So if this angle up here is 90 minus theta, it tells us that this angle in here must be theta. So we can now use trigonometry. Let's label these sides, say parallel and perpendicular. And so to work out the length of that perpendicular side, we can use cos theta is equal to adjacent, which is our perpendicular side, over the hypotenuse mg, which tells us that our perpendicular side is equal to mg cos theta. And for our parallel side, we can use sine theta is equal to opposite, which is the parallel side, over mg. So this tells us that our parallel side is equal to mg sine theta. So we now have split our weight force into two components. Here we've got mg sine theta, which is what's pulling it down the plane. And here we've got mg cos theta, which is what's pushing it into the plane. Now, what we can do with this perpendicular component is we know that in the direction perpendicular to the plane, the forces sum to 0. How do we know that? We know that because it's not accelerating up off the plane or down into the plane, because we could see it was traveling straight down the plane. So this tells us that we've got the mg cos theta acting down into the plane. The other force which is involved in acting on our trolley is the normal force. So this tells us that the normal force must be equal to mg cos theta. So that's how we show this with breaking it into components. Now, in the direction parallel to the plane, we only have one force, and this force is equal to mg sine theta. So because this is the only force, and it must be equal to ma, and so we end up with A is equal to g sine theta down the plane and parallel to it. So let's test this out now. So what you can do with students is use a program such as Tracker or data loggers to check the acceleration of a cart down a plane. Now this plane is currently set up with an angle of 3 degrees. So let's let our cart run down the plane. Now we can use the Tracker program to calculate the acceleration of the cart as it moved down the plane and check, is it equal to g sine theta? Okay, let's watch this in Tracker now. So our top graph is the acceleration versus time graph, and the lower graph is the velocity versus time graph. So you can see for the velocity versus time, we've got a fairly straight line. For the acceleration versus time graph, we've got a fairly flat line, which is what we expect along here until the cart comes to the end and I stop it, at which point the acceleration starts going a little strange. Let's choose one of our points now. So this one looks like it's relatively central on the good line there. And so at this point, the acceleration is 0.511. Now, we showed that the acceleration down an inclined plane when there was no friction was given by g sine theta. If we put into a calculator 9.8 times sine of 3 degrees, we get 0.513. So that's in very good agreement with 0.511, which we measured here.